All right, let's get started. What did we discuss last class? We're talking about matrix inverses. Okay, what did we talk about? Yeah. Sorry? Okay, all right. So if you're talking about matrix inverses, it has to be a square matrix, full rank, and then you have a unique matrix A inverse such that A inverse or A inverse A equals In. Okay. What is A inverse? What is the interpretation of A inverse? What does it allow me to do? Yes. Assuming the columns of A come from the standard basis, it allows me to allows change of basis from from what? From what basis to what basis? Sorry? No, no. See, this is in the standard basis. The columns are in the standard basis. So what does A inverse allow me to do? To the basis formed by the columns A. How do we know the columns of A form a basis for Rn? No, that's a valid question, no? How do we know the columns of A actually form a basis for Rn? Okay, are they linearly independent? Are the columns of A linearly independent? Yes. What? Yeah, it's full rank. That means the rank is n. That means there are n linearly independent columns in rows. So it is full rank. So it does form a basis for the columns of A. The columns of A do form a basis for Rn. Okay, and what basis is X in? Sorry? No, no. Yeah, this is in the basis uh, formed or basis of columns of A. And what does it represent in the basis of columns of A? Which vector does it represent? B, it represents B, right? So X is the representation of B in the basis formed by the columns of A, where B is in the standard basis. Is it clear? Okay, all right. What else did we talk about? Sorry? Sorry? Ah, yes. So rectangular matrix. Full says A is P cross Q. Okay. If you have a rectangular full rank matrix, can you have an inverse? In this sense, that means you multiply both pre and post, you get In. If it's rectangular, right? If it's rectangular, you can only have a left inverse or a right inverse. So when you have a tall matrix, what can you have? You can only have a left inverse, C, and what will this give me? IP or IQ? Q is less than P. What about this? So you can only have right inverse and this. See? And are these unique? The left and right inverses for matrix A. This is not unique, is it? That means there are infinitely many right inverses. What about left inverses? Left inverses are unique? No. In both cases, there are infinitely many right inverses. Okay. And then we then talked about two special uh, left and right inverses, right? The pseudo. Okay. What is the pseudo inverse of A when it's tall? It is always represented as. Okay. And what about when it's fat? It was fixed. What is special about them? What is special about this and this? This is just one possible C, and this is just one possible B. Right. Well, C is not this is not orthogonal projection matrix, but A dagger. This is the orthogonal. Did you guys have a chance to verify that this is in fact equal to Q transpose, where Q is the QR decomposition? Okay, do that if you've not done it already. Okay. And what about this? Right. When you have a fat matrix, Ax equals B has infinitely many solutions. If you take any right inverse and multiply it by B, and if you multiply this by A, this will always give you B. Okay, that means capital B, a right inverse of A multiplied by the vector B is always a solution. That means there are infinitely many solutions. And this one gives me a special solution where X cap is A transpose A, A transpose inverse B. And this, the second norm of this vector is minimum of all possible. Okay, that's their specialty. And then finally, what did we talk about? Sorry? Right, he is not full rank. Can we ever get identity matrix IP or IQ if it's not full rank? Let's say the rank is R. We cannot. What can we get? If you have A multiplied by C, what can you get? All you can get is this, or if it's fat, this is all you can get. And what about solving for Ax equals B? Well, same thing. If B is in the column space of A, then you can solve this. But there'll always be unique solutions. And in fact, if B is not in the column space of A, then of course you cannot solve this. You can find an approximation of B, but there are infinitely many possible x's that will give you the approximation that you want. Okay. All right. This is what we covered last module. Today, we will look at an application of these ideas in signal processing. Okay, I'll remove this. I'll leave this for now. Okay. All of you have had signals and systems in your undergrad? Yes? Okay. What is a signal? Yeah. Right. This is simply a function of, let's say for now, let's call it time. Okay. Some independent variable, but for us it's time that carries some information, carries some info, right? Let's say we are recording some signal as a function of time, and let's assume that we're talking, and for this discussion, we will only be talking about discrete time signals, okay, which are usually written like this, okay. X of n represents the signal of interest, n is time instant, and n is an integer, okay. Now, you can have infinitely long discrete time sequences or discrete time signals, but in practice, we always only deal with finite duration signals. Let's say, so our discussion also will only be for finite duration signals. Means you have a signal x of n, okay, and for convenience, we'll always assume that time variable, the time instant n, is always between n and some capital N. Capital N is the total length of the signal, okay, and your small n is your time instant. So your x of n is only defined for this time period, because this was the time period of interest over which you recorded the signal, and it's of finite length. So x of n is simply a bunch of numbers, right? X of 0, x of 1, x of 2, so on and so forth. And the last value is x of n minus 1. Okay. It's customary to have time index start from 0 in signal processing. That's why we write it like this. You might find that some people might write it like this. Their first time instant could be 1, but in our case, we'll always say the time n starts with 0 for us. Okay. And that's why the last one is x of n minus 1 and not x of n. See, if it's just a bunch of numbers like this in a particular order, we've already come across things like this, right? Where you have a set of n numbers that are in a particular order. What are those? Very first lecture. No, just a list of numbers. No, n vectors, no? Yeah, column vector, n vectors, no? Right? Just a list of n numbers. So we can think of the signal x of n now as a n vector. Okay, and let's assume for now that the signal takes on only real values. Okay, that means my x of n, I could write it as a column vector. The first value is x of 0, second value is x of 1, so on and so forth, and x of capital N minus 1. Okay, and this is simply an element from my vector space Rn, right? And in Rn, so if this is Rn, okay, and let's say this is the origin of Rn, this signal x of n, and for now let me call it x, is simply a point in this high dimensional space. And this arrow essentially represents this entire time signal is simply an arrow in my n-dimensional space. Okay, and because we are able to think of time domain signals as vectors in high dimensional space, now a lot of ideas that we've discussed so far about vector spaces, many of them can now be applied to signals to understand them a little better. Okay, the real jump is this: if you have a finite dimensional signal, you can think of that entire time signal as a point in a high dimensional space. Okay, and this arrow essentially represents that point. See now, I'm calling this a time domain signal because this the value assumed by the signal or value taken by the signal is a function of this variable n, which represents time. Or one way to think about this is if you think of the signal as a table, at time n equals 0, this takes some value -1, 1 it takes 3, so on and so forth, and -1 it takes some value, let's say -11. Okay? These numbers here that you have, these n numbers, are associated with a specific time index. That's why I call this a time domain signal. Because this is at time t equals 0, 1, 2, and so on and so forth, at time n minus 1. And in the last class, I said you can talk about geometric quantities like this, but the moment you assign numbers to them, you need a reference, you need a basis, right? In the case of time domain signals, that basis is essentially your standard basis. Okay, so this signal that I've written, x of n as a vector x, is simply, and what is the standard basis here? It will be E1, E2 till E capital N. Right? So this vector x, I can write it like this. Vector x is simply, how do I express x in terms of the standard basis? Okay, what will be the first? C, is it? Where is C here? E1, okay. E1 into what? X of 0, right? X of 0 plus, so x of 1 into E2, so on and so forth. And you get x of -1 an. Okay, so this vector can be written like this in terms of the standard basis. And what is EI? In fact, what will be this thing when you write it down? It will simply be x of 0 and all zeros, right? Because it's x of 0 multiplied by E1 plus, what is this? It's 0, x of 1, and all zeros. And if you add all of these together, you do get that, right? So this is the representation of your of this vector x or your time domain signal. And the basis that we've used here is essentially the standard basis. Right? And the standard basis are some vectors like this in your Rn. There are n of them. Each one has a length 1. So let's say this is E1, E2, E3, E4, and so on and so forth. And all of them are orthogonal to each other. Standard basis forms an orthonormal basis. What signal do the... So if, I started with the time domain signal and I said, you can think of it as a vector. And then I'm saying, well, this vector is represented in some basis. And that basis that we're dealing with is the standard basis. And I've written down n unit vectors as the basis vectors for this basis. Then, if you take E1, right, what kind of a time domain signal does E1 represent? If signals represent vectors, I can ask what does a particular vector represent in terms of a time domain signal? Is the question clear? No. Okay. We started with the time domain signal, and I said you can think of the time domain signal x as a vector in Rn. E1 is a vector in Rn. I'm asking you, what is the time domain signal corresponding to E1? Okay, let's write that. So what is the E1 of n? What does this signal look like? If I were to plot this, or let's write it down. What will be the values attained by this signal? What is the length of the signal? Sorry, not the length, but how many elements does it have? Capital N, right? What and it has, that means it's represented by n numbers. I'm asking you, what are those numbers? In, what do you mean? You're right, but what are the values for E1 of n? It's 1, 0. Okay. What about E2 of n? Okay. See, this is time n equals 0, right? This is nothing but the discrete time version of your impulse function, which is 1 at time t equals 0, 0 elsewhere. Because we're only looking at time from time 0 to capital N, we don't have to worry about what is outside, but this is essentially your del of n. What is E1? Oh, sorry, that is E1. What is E2? Right. So on and so forth. The last one, En, yeah, capital N. Is that correct? That's it? Minus 1 or plus 1?
Can you take value? What value 10?
This one?
Yeah.
You remember unit vectors from the very first lecture? What is the unit vector E? Ei. Let's say this is from Rn, right? All elements are 0 except for the ith value, and the ith value is 1. Okay. Okay. That means, so if I represent my vector like this, that means I'm saying that my time domain signal can be written as x of 0 into delta of n plus x of 1 into delta of n minus 1, and finally x of n minus 1 into delta of n minus capital N plus 1. I mean, this is how you write. I mean, this is how a time domain signal is represented as a linear combination of time shifted impulses, right? We've essentially translated this idea into talking about into thinking about signals as vectors, and talking about any signal or any time domain signal as a linear combination of um, time shifted impulses. In the vector space language, this is simply the linear combination um, of the vectors from the standard basis. Is it clear? Okay. See, if that is the case, right? We've seen when we talked about vector space, if x is some vector in Rn, and this is the standard basis, is just one of the possible bases for your vector space, right? There are lots of other possible bases that you can, in fact, infinitely many bases you can choose. The question is, okay, if my time domain signal x of n has this representation in the standard basis, are there other bases in this space that give me, I mean, obviously they'll give me a different representation for my original signal, but maybe those other bases will tell me something that is not immediately clear from the standard basis representation. Okay. Now we will before we proceed, right? Before we go to the next step, we will cover something that is important to talk about the rest of the content in this module. So far, we've only talked about vectors and matrices that are whose elements are real numbers. Okay, but now we will have to deal with complex numbers. Okay, so we'll take a small detour, uh, talk about complex numbers, and then matrices and vectors in Cn. Okay. and then the slight differences in definitions of inner products and all that. Okay, when you're dealing with complex numbers. Uh, what is a complex number? What is a general or a standard form in which you write a complex number? Well, you usually write it as JB. I mean, in maths it's I. In electrical engineering it's J. I will stick with J because I'm used to writing it in J. So, but whenever you see J, I'm simply talking about I, the imaginary number. Okay, what is J? J root of -1. That means J square gives me -1. Where are A and B from? Where are A and B from? Well, they're in general real number. Okay. In fact, when B is 0, let's say I call it Z. Z is a complex number. Z is simply a real number because this is A plus J times 0. This is real number. And when A is 0, then I get 0 plus JB. This is a imaginary number. Okay. If real numbers are represented by the real line, complex numbers of this form, because you have two numbers, are represented by the complex plane, where this horizontal axis is your corresponds to the real component, which is usually written as real of Z, and the vertical axis is your represents your imaginary value, where if you have a complex number Z, this function RE applied on a complex number will simply give me A, where Z is A plus JB, and imaginary of equals B. I mean, I'm sure most of you know all this. For people who've forgotten uh, complex algebra, this is just a very brief review. Okay. So, if you're talking about real numbers are represented as points in the real on the real line. Complex numbers similarly are represented as points on the complex plane. Now, if you have a complex number A plus JB, that's simply a point here with coordinates A and B, and it's also customary for us to represent it by an arrow. Okay, where if you drop a perpendicular from here to here, this will be A. If you drop a perpendicular from here to here, this will be B. Now, because we can think of complex numbers as vectors in the complex plane, we can talk about the length of a complex number. What is the length of a complex number? Or the magnitude of a complex number? What is the magnitude of a real number? If you have, let's say, some R, which is a real number, what is the magnitude of the real number? No, magnitude of the real number. Well, norm 2 is, okay, you can take the norm 2 of this. That's simply the absolute value of R. That simply tells you how far away is this point from my origin, irrespective of which direction it is in. We can similarly talk about the magnitude of Z belonging to C, and that is simply given by the modulus operation or the modulus of the complex number, which is nothing but you take simply the Euclidean norm, which is basically A square plus B square, right? There is another useful operation when you deal with complex numbers, which is called the conjugate, conjugate of a complex number Z. What is the conjugate of a complex number Z? If Z is a complex number, that is A plus JB, well, either Z star or Z bar is simply A, you negate imaginary component. Get this. And one of the reasons this is useful is now you can compute the magnitude of a complex number as simply the magnitude square of a complex number is simply z multiplied by z stars or z bar, doesn't matter. But that brings us to another issue. What is the product of two complex numbers? If you have two complex numbers, z1 equals a plus, so a1 plus j b1, and z2 equals a2 plus j b2. What is the sum of two complex numbers? Z1. You simply add the real and imaginary component. This is simply a1 plus a2 plus j times b1 plus b2. What about, sorry, the product of two complex numbers? Well, it's simply a1 plus jb1, a2 plus jb2. And if you multiply this out and simply multiply, you take this, multiply each of these elements by the first one, the second one, and if you simplify, what will you get? A1, A2 minus B1, B2 plus j times A1, B2 plus, okay. How do you divide? How do you divide two complex? Can you divide two complex numbers? Right, you can. All you do is multiply both the numerator and the denominator by z, the complex conjugate of z2. This is just simple regular multiplication of two complex numbers. Okay. See, the way we've now represented this complex number z, right, is in the Cartesian form, okay, where we've talked about represented this vector as two components, one along a horizontal axis and another one along the vertical axis. There is another form to represent this, which is the polar coordinate form, okay, where let's say this angle is theta, and let's call this distance r, the length of this vector to be r, that means equal to r. Then if z equals a plus jb, if this is the Cartesian representation, you can also write it as what? Well, if z is represented by a comma b, we can also represent it as r comma theta. Okay. In fact, we can represent both a and b in terms of r and theta. What is that? This will be r cos theta, this j sin theta, or we can write it as r. I'll just write it as c theta. Okay. It turns that this actually simplifies to j theta, and then that in fact is a very popular way of writing complex numbers. Okay, all right. This is most of what you need to know about complex numbers for now. Now, let's talk about complex vectors from the complex plane. So, if we are talking about Cn, that means a set of points that are represented by n complex numbers. If you have a complex vector x, then you have x1, x2, xn, where each xi is a complex number. Okay. The same rules of addition and multiplication work, addition and scaling work here. If you add two vectors from Cn, you simply add the corresponding elements. And when you say you're scaling x by some number, now this can be a complex number. Okay. That means I multiply each of my elements by this complex number alpha. What is the definition of the standard inner product in Rn? So in Rn, we have two vectors x, y, both from Rn. What is x? What is the standard inner product? It is represented like this, right? What is it equal to? Sum of what? So, xi, yi, summation over capital N. Now, instead, let's assume that x and y come from Cn. The definition of, see, in the case of vectors from Rn, this was the definition of the standard inner product. The standard inner product was commutative, right? It doesn't matter which way you write it, both of them will give you the same answer. When we talk about vectors from Cn, this transpose operation is slightly different. If you have a vector x from Cn, the transpose operation now gets called the Hermitian operation. Okay. Now let's say x was a column vector. X transpose was simply a row vector, right? X Hermitian, when x is a complex number, where, well, x is a vector from Cn, is a row vector, but with one change. You take the individual complex numbers, you don't just write x1, x2, well, you write x1, but you also take their complex conjugates. Okay? And the standard inner product now is not, if x and y are from Cn, is not this anymore. The standard inner product is this. And what will this be equal to? X Hermitian multiplied by y. See, sometimes you might also see expressions where people write the Hermitian operation like this with an asterisk. So if you see this, you know what they're talking about. What will this work out to? So this is essentially x1, x2, xn, y1, y2, yn. This is essentially I equals 1 to n, xi bar yi. Okay, so you don't just multiply the individual components, you take the complex conjugate of whatever you're taking the Hermitian of, and then multiply it by the element from the other. This also means x Hermitian y is not equal to okay. In fact, this is equal to y Hermitian x, the whole conjugate. So x Hermitian y and y Hermitian x will be complex conjugates of each other. That is one big difference when we're dealing with Cn and in terms of the standard inner product. Now, one thing that will happen is Rn is contained in Cn. Okay? If you simply have all of these as real numbers, these are still complex numbers with no imaginary part, right? The Hermitian operation will simply become the standard inner product. So this is in fact the more general version of Cn is a more general vector space because it contains Rn. Okay? So you can think of this as the most general definition of the standard inner product, and Cn being the more general vector space than Rn. Okay? So this is something to keep in mind. Well, then see the concept of bases, subspaces, and all of them remain the same. Now, if you have an orthonormal basis for Cn, let's say I say U1, U2, Un is an orthonormal basis for Cn. What does it tell me about the individual vectors? What can you say about 1 when j 0 j? Correct. Okay. That's all I wanted to say about uh, complex or vectors from Cn. Now let's move to matrices. Okay. Same thing. The elements of A are now are complex numbers, not real numbers. The transpose operation is now mentioned. Okay. This will be C of Q comma Q cross P. You switch the rows and columns, and you take the complex conjugate of the individual elements. Okay. Now, if you have a set of vectors that form an orthonormal basis for Cn, and if you now put them in a matrix like this, if you had an orthonormal basis for Rn and you wrote them in a matrix like this, Q1, Q2, Qn, what is this matrix called? It had a name. What kind of a synthesis Q? This is called an orthogonal matrix. What is special about them? Well, the columns form an orthonormal basis, but there's one more thing that's special. Q inverse is Q transpose, right? This is the complex equivalent of an orthogonal matrix. These are not called orthogonal. These are called unitary matrices. I don't know why this specific name, but these are called unitary matrices. Okay. And U inverse will simply be what? What do you think U inverse will be? Yes, it will simply be. This means if you have U Hermitian U, this gives you I, which is equal to U. Okay, it's just these. Now we move on. Yeah. Okay. So remember, before we took the detour, we said we can think of a finite duration discrete time signal as a vector in Rn. Okay, and because Rn is contained in Cn, we can think of a real time a signal x of n, even though let's say it only takes real values. We can think of this as a vector in or x in Cn in the complex state because Rn is contained within this, right? And we said, well, the time domain signal can simply be thought of as a linear combination of the standard base or the if you have a time domain signal, the corresponding vector can be simply thought of as a representation of the time domain signal in the standard basis. Then we started asking, are there other bases where we might be able to see the signal from a different perspective, right? Turns out there are, and the most popular one is the Fourier basis. or maybe the oldest one. Okay. How many of you have come across Fourier series and Fourier analysis before? Everyone. Okay. Do you remember Fourier series? What does the Fourier series say? Or what is the general idea behind a Fourier decomposition of a signal? Right. So a signal x of t can be represented as a sum of sinusoids of different frequencies by appropriately choosing the amplitude and phase of each of these frequencies. You can add them all together and get x of t. That's the general idea. Right? Or another way to think about that is uh, the Fourier representation is a way of representing signals in terms of uh, rhythmically varying signals, and sinusoids represent signals that are rhythmically varying. Sorry, this keeps disappearing. Okay. And because, so we said time domain signals can be thought of as finite duration time domain signals can be thought of as vectors in Cn. And if you have sinusoids that are of finite duration but different frequencies, these would also be vectors in Cn, right? This would be, so if this is Cn and this is my original time domain signal x, maybe or each of these would be arrows in my space Cn, right? And if you're talking about sinusoidal signals, it turns out that these are just not some arbitrary arrows or these are not just any arrows in Cn, but these in fact have a very nice property. Okay. So now, if you're dealing with a finite duration signal, there are n. So we are talking about signals in Cn. There are n sinusoids that we can talk about whenever you're talking about a finite duration signal of n samples. Okay, those n sinusoids can be written like this. Can be written in this form: e power j 2 pi k divided by n of n. Okay, and I'll call this some time domain signal wk of n, where n k here simply represents frequency. Okay, and if you expand this out, this is simply cos 2 pi k by capital N n, this j sine. Okay, k represents frequency and n is simply your time index. Okay, you can do Fourier analysis without ever dealing with complex numbers. Okay, but using complex numbers is simply a way to make the maths a little easier, because when we talk about Fourier analysis, right, decomposing a signal into sinusoidal components for of different frequencies, you always have to choose two numbers for each sinusoid. What are the two numbers? You have to choose for any frequency how big, what is the amplitude of my signal, and what is the phase of my signal. That means you have two numbers that you have to choose, ak and phi k. These two numbers are essentially compactly represented by a complex number, because a complex number has two real numbers. That's all. The reason complex number, you always see Fourier analysis represented in the complex domain, is because the maths is simpler to write. Yeah? And in fact, complex numbers too have amplitude and phase. Any complex number has a length, that is basically how much of the sinusoid you take, and this angle theta is the phase of the sinusoid. That's why complex numbers are preferred. So you can think of this as simply a compact way of representing a sinusoid of frequency k. Okay? Okay. And it turns out there are n of these. You don't have infinite number of sinusoids like this. if you're talking about only finite duration signals, there are exactly n of this, w of 0 of n, w of 1 of n, w of capital N minus 1 of n. There is no more. Okay. If you choose a value of k that is greater than n minus 1, you essentially come back to w0 of n. Okay. So it turns out if you're dealing with finite duration signals, these are the only sinusoids possible. There are no other sinusoids possible. Okay. So we have these n possible sinusoidal signals, and each of this represents a sinusoid of different frequency. Okay. That means for finite duration signals of length n, there are only n frequencies that are possible, nothing else is possible. Okay? And that's what I've written here. And it seems like a nice coincidence, right? We're talking about a vector space of dimension capital N, and there are only n sinusoids that are possible. Sounds like this might have to do something related to the basis for the vector space, and in fact it is. So if you take these signals, now each of these signals we can think of it as a vector, right? So w of 0, w of 1, w of n minus 1 in Cn. Okay, and in fact this set turns out it forms an orthonormal basis for Cn. That is why the Fourier basis is one of the special bases, because the sinusoids form, interestingly, an orthonormal basis for Cn. In fact, you can show that. We will not go through the details. If you take, it looks like I've used the star signal here for complex conjugate, for the Hermitian operation. If you take any of these, right, W0, you take Wi, take the Hermitian, Wj, turns out this will be equal to capital N, when I is equal to j, and it will be equal to 0. That means each of these vectors are mutually orthogonal to each other. And Wi, Hermitian Wi, is simply the square of the length of Wi. It's simply the 2 norm of Wi square, and this is equal to n. So it's not of unit length, but we can normalize it if we divide each of these by 1 by root n. Each of them will have unit length. And in fact, if we divide each of these by root n, so it's not an orthonormal basis, it is an orthogonal basis, but if you divide each of these signals by root n, you get an orthonormal basis for C. Right? So if that is the case, right, and I have my original time domain signal, x, okay, and what basis is this represented in? My original time domain signal, the standard basis, right? Right? And the standard basis correspond to time shifted impulses. Okay. Now I have this Fourier basis, and let me write it down as W0, W1 minus 1. This forms an orthonormal basis for Cn. I can now ask, if this is the representation of my time domain signal in the standard basis, what is the corresponding representation of my signal in the Fourier basis? Right? That's a valid question to ask, right? Now the question is, how would you switch? How would you go from the standard basis to the well, this is the Fourier basis. Well, you take this and then you form a matrix W. What is the shape of this? What is the size of this matrix? This will be n cross n. Okay. There are n columns. Each of this is an n-dimensional vector, so it's n cross n. Well, we stick a root n outside. W would be a unitary matrix. right? Because the columns are orthogonal. If I put the 1 by root n, the columns are in fact form an orthonormal basis for Cn. That means this is a unitary matrix. That means U emission, W emission will give me I. Now the question is, if X is my time domain signal, that means X is a representation of my X is represented in the standard basis. How would I get the corresponding representation of my time domain signal in the Fourier basis? How do we switch basis? Inverse, right? Right. That means that I think I've used the symbol F for the matrix. So maybe I'll stick with F instead of W to stand for Fourier. F capital N. Inverse of what? So I have my X, which is in the standard basis. I want my representation of X in the Fourier basis. The subscript stands for X being represented in the Fourier basis. How would I get this? Yeah. W, not W, Fn inverse, right? Fn inverse, but because it's unitary, the inverse becomes simply the Hermitian operation. Okay? And this is essentially your discrete transform. You remember the expression from DSP? If x of n represented your time domain signal, what was x of k? Remember, k is the frequency index. How did we compute the kth frequency component of your DFT from your time domain signal? Well, instead of W, in terms of complex exponentials, and here, is it k or n? Okay. Now, what does this look like? It's summation over n numbers multiplied by two complex numbers. We just saw something like that earlier. I wiped it off. Not linear combination. This is nothing but it's simply the inner product of your WK, this one, with X. You see this negative sign? That negative sign comes about because you've taken the Hermitian. Okay. And if you find the K element here, that will exactly be this. That will work out to this. So this is in fact the discrete Fourier transform. Okay. Maybe this is, this is how at least it's covered in undergraduate DSP. But now you have a different way of looking at this. What you're doing here is your time domain signal is some vector in this Cn space. All you're doing now is you're looking at the same signal using a different basis. That's basically your Fourier basis. Okay, and so it's a representation of the same signal, but in a slightly different, with a slightly different reference. Yeah. So if you had the Fourier representation, how would you get the original time domain signal back? So I have xf. I think simply take this fn, and that will give me my x. Okay. In fact, you got xf by solving this equation, right? Ax equals b. You get x by doing A inverse b. That's what this is, A inverse b. The only difference is there is no 1 by root n here. the the n is taken care of in the inverse DFT, where instead of having 1 by root n here and 1 by root n in the inverse has 1 by n. That's all. And if x was in the standard basis and this was the time domain representation, this is representation of this x in the Fourier domain, and this is called the frequency domain representation of your time domain signal x. Okay. Let's just look at an example. Let's say we're looking at some signal like this. Okay, this is some data that I pulled out from some US database. Right, it's measure of some variable x, so vehicle distance traveled per month, which is plotted along the y-axis. On the x-axis, these measurements are taken every month over a period of 14 years. I've seen plotted time domain measurements that were taken every month. Okay, so this is essentially your x of n. Okay, and each of these circles that you see is the value attained by that signal at the specific time point where you measure it. Right now, if you look at it, what do you see in this? What all characteristic features do you see in this data?
There is a bit fact, let's say, more than half of every cycle.
Right. Notice that each of this is 2 years. Each of those marks is 2 years. That means it looks like first thing you notice is well, the y-axis is huge, the value compared to the min and max of the signal. The y-axis value is or the value of the signal is quite large. Okay, the average value of the signal compared to how much. See, this variation is about what? 20,000? No, 60,000. Okay, but that whole thing starts from the average value is about 2.4 lakhs or something like that. So the average value is quite large. There seems to be a rhythmic pattern to this, where you see uh, in January it starts at a low value, goes up and comes back down to a low value in January. So that's one of the rhythmic patterns you see. And on top of each cycle or for each year, there is also some variation that goes on. Okay. So it looks like this data does have some rhythmic pattern to this. So it is an ideal candidate for looking at this signal from a different perspective, using a basis which has rhythmic basis whose have these rhythmic patterns. So now, if right, okay. Now let's say we take that x of n. We uh, the there are about, I think, 240 points or something like that. We form the Fourier matrix, and then we compute this. Okay, fn. Basically, we do the Fourier decomposition to get xf. What I've plotted here is essentially your xf, each of the k components, 1 to n, and their magnitude. Each one is a complex number, remember, and their magnitude. So you can think of the x-axis as a different case. Right? There are about 240 points there, I think, or something like that. So we're dealing with the time domain signal that is, no, it won't be 240. So that's 15 years, 12 points. How much is that? 120, 180 points. There are 180. Okay, so we were dealing with the time domain signal that had 180 points. If you do the Fourier decomposition, you get another vector which has 180 points, and each of these values corresponds to a different frequency. The very first value corresponds to 0 frequency. That means it's a constant DC signal. A signal does not change at all with time. The second one corresponds to the lowest possible frequency. The third one corresponds to the next harmonic, and so on and so forth. That's the K. Okay. Now, if you take the Fourier transform, you see something like this. There is a huge component at k equals 0, and then everything else is fairly small, and you see this little bumps. Why do you think that happened? What about your original time domain signal could have resulted in a weird looking XF like this? Remember, I earlier said there are two things you can notice in this. It has this rhythmic variation component, but the average value is quite large. Okay, the average value is about 2.2 lakhs or something like that. Okay, so it looks like the average value of the signal essentially dominates every other component there is, right? So you have a huge value for the signal, and then tiny variations about that huge value essentially tells you that the major component is this average value. These tiny components don't appear if you take this average, large average value into account. So it seems like it does make sense that the signal has a large average value. Let's say we remove the average value. We want to look, what we are more interested in is this rhythmic pattern itself and not the average value of the signal is. So I take the signal, I compute the average, and I subtract the average out. That means it has no DC component anymore. I'll come back to this later. Right. I take the original signal, I remove the mean. Okay, so now you see this is varying about 0. And now if you take XF, the Fourier decomposition, the first value will of course be 0 because I've deliberately made the mean of the signal to be 0. And now you do see that there are some spikes here, which basically tells me, so this is the way to read this graph is the height of each point tells you how much of a particular frequency there is in your original signal. Okay, and whenever you have a signal like this, where you have most of the signal is close to 0, but you have these spikes, that means you have specific frequency components that are there in your signal. And that's what we see as well. In fact, if you look at the largest frequency component, it's about 0.9. Okay, and uh, the units for the axis is cycles per month because you're making the measurement every month. In fact, that is very close to 1 cycle per year. Okay, and that's essentially what you see every year. The trend you see in that signal is this, one of the trends. That means you have 1 cycle every year, and that in fact comes out a lot more clearly in your when you do the Fourier decomposition. Okay, so that's the major component. In addition to that, you also have a few other frequency components that are riding on top of this, and those are higher frequency components because they vary much faster than 1 year. The most dominant rhythmic pattern you see varies at around uh, 1 cycle per year. The other ones have smaller amplitude and they vary a little faster, like this. Right? So by doing the Fourier decomposition, what we visually observed now comes out a lot more clearly when you do the Fourier decomposition. So when you do have a signal that's got some rhythmic pattern, then decomposing the signal or representing the signal in the Fourier basis gives you a much more clearer view of this rhythmicity in your data at different frequencies than directly looking at the time domain signal. There are a few other details that are there in the slides. What I show here is only the magnitude of each of these components. Okay. Now remember, each of these components has a cost term and a sine term. Okay? I mean, you can look at those individually as well, but I won't go into those things in class. You can go through them, and if it's not clear why this is negative and there is no sine component, so this is the cost component, this is the sine component. If you're not able to make sense of this, you can always come and talk to me, and then we can discuss about why the graph might be this way. Right. So with that example, what I wanted to demonstrate was when you have a time domain signal that's got some rhythmic components, the Fourier basis is actually a nice basis to decompose the signal in or to represent the signal in, because some of these rhythmic components will come out nicely. That also means if you have signals that don't have a rhythmic nature, okay, then it turns out the Fourier basis is not a good basis. For example, imagine you had a signal like this. Okay, what I'm trying to show is something like this. Specifically, a signal that is short-lived in time. Okay, it does not occur for all time. What I'm showing there is a signal like this, and with some noise on top. Okay. Now, if you take this and then you do the Fourier decomposition, okay, what you find is what I've shown here in the second graph. Ignore the third one, second graph. All this tells me is, I mean, if you look at that plot, it looks, this is frequency, it has this shape. All it tells me is there is a lot of low frequency components, and there aren't a lot of high frequency components. That's all it gives me. It does not give me any special insight into what the original signal was. Okay. In fact, the worst thing is, let's say you had one signal like this and another signal that is more or less similar, okay, but time shifted. If you do the Fourier decomposition of this signal and you compute the magnitude of each of those components, you might get something like this. If you only go by the magnitude spectrum, you would say, well, both the signals are the same, but clearly they're not the same. Okay, this signal is very different from this because something interesting happens here at this time, whereas here something interesting happens here. Okay, whereas if you look at these two signals from the Fourier basis, it looks like Fourier basis tells you I don't see a difference between them. So looking at the signals using the Fourier basis is not really a good idea. Okay, and the reason for that is if you look at the Fourier basis vectors, right? All of these vectors, if you plot them, let me just, uh, yeah, let's say we're dealing with finite duration signals of length 0 to capital N. W0 will simply be a signal like this, constant values. W1 would be something like this. W2 would be something like this, and so on and so forth till Wn. Now, if you look at all of these signals, right, all of these signals have some value for all time, right? Whereas if you look at these signals have some value for a short duration of time, and then they're zero everywhere else. That means the signal that you're trying to analyze does not look like any of these. That is why if you want to represent something like this, you have to do a lot more complicated scaling and scaling of each of these moments and add them together to get this. You don't have a nice clean representation. Whereas in the original data, in the previous data, which had a lot of rhythmicity, you had a very nice representation like this, which showed that you only have, that the signal has these 3 or 4 major frequency components. And that does not appear here because the signal that we're trying to analyze with the Fourier basis does not look like any vector in the Fourier basis. Okay, that's why the representation that you get is not very insightful. Okay, okay. So with that, we'll stop here, and then we'll take up the rest of it on Thursday. Okay, thank you.